All right, good morning, everyone. I hope you had a good weekend. So, let's see, announcements. We didn't have a homework due last week, but we do have one due this week. The due date is Good Friday. I just kept it on Friday, but Friday is obviously a holiday. If you want to get it done before the holiday, please do that. We're doing our last lab of Physics 121 this week. And so there is a pre-lab, so please get that done. Bonus project, April 8th is the deadline to get me your YouTube video link. And then finally today, I usually have office hours, but I had to cancel it because of some other conflicting meetings. So I'm going to extend office hours tomorrow from 12 to 2. Okay, the main goal for today is to get prepared for lab number 8 this week. And so what I want to do is I want to kind of motivate. Oh, let's see. Can I get rid of this? How do I get? Okay, there we go. So I want to motivate what we're going to do for lab 8 and sort of just give you a general idea of what's going to happen during that lab. So the first thing that I want to talk about is the fact that we've seen now if we have a charge distribution that's changing. So let's imagine we start with some distribution of charge and then it changes. Well, the only way you can change a distribution of charge is if there's some motion or some flowing of the charge, so some currents. And we know that currents are a source of magnetic fields. So what we know already is that a changing distribution of charge creates magnetic fields. And this changing distribution of charge really is just another way of saying currents are going to, oh, sorry, I don't know what's going on. Stop it. Okay, here we go. So currents create magnetic fields. So what lab 8 is going to be about is the inverse process. So let's imagine now that we have just a constant magnetic field. That doesn't do anything. But now if we say our magnetic field is going to be changing, then we can use that changing magnetic field to create currents. Okay, so that's the idea. So today, we will see that changing magnetic fields can create currents. And so this effect, this phenomenon has a name and it's called Faraday's effect. Okay, so what I want to do is I want to start by doing a couple of short demonstrations to try to show this effect here. Do you guys have a question over here? Do you have a question? No? Okay. All right, so to do that, what I'm going to do is I'm going to try to share this screen here. So let's share, and I'm going to start the video. Okay, so people on Zoom should be able to see this little apparatus. So for those of you here, you can either look at the video in the little square there, or you can look in front if you're close enough. So what I've got is this little plastic ring. It has a bunch of wire. So it has a thin wire that's wound round and round and round and round, and then it's covered up with some tape. This black and red wire coming out here are connected to the coil. And then I have a couple of what are called LEDs, light emitting diodes. So there's one green one and there's one red one. And so what you need to know about LEDs is that they light up if current passes through them, but only if they pass through in a certain direction. And these two LEDs are arranged so that if current flows through our coil in one direction, the red one will turn on. If current flows in the opposite direction, the green one will come on. So they'll never be on at the same time. So if we see red and then green, it means that the direction of the current has switched. The other thing I have are some strong magnets. These are rare earth neodymium magnets, and they're the same types of magnets that you're going to be using in the lab. You'll actually use a slightly bigger one. So all I'm going to do is I'm going to first just put my magnets inside the coil, and nothing happens. The LEDs aren't on. And so a static or constant magnetic field does not create a current or motion of charge in our coil. So now what I'm going to do is I'm just going to pull it out, and I'm going to pull it out pretty quickly, and I want you to look at the LEDs. So let's see if we can do this. So which one came on? Green one comes on, okay? So if I pull this out of the coil very quickly, the green LED comes on. What I'm going to try to do is I'm going to try to push it in very quickly. We'll see what happens if I can do this. Okay, so if I go in quickly, the red one. If I pull it out quickly, it's the green one. So the direction of the current changes depending on whether or not this magnetic field is increasing in the coil by pushing it in or decreasing by pulling it out. So that's a demonstration of the fact that a changing magnetic field through a loop of wire creates a current. And so that is called Faraday's effect. So I'm going to do another sort of demonstration here. Let's see if this will work. Yeah, that's good enough. So I've got a plastic tube and I've got a copper tube. They have the same inner diameter, and the magnets fit easily inside these tubes. So they can fall through the tubes without touching the walls. There's no friction or anything like that. So the first thing I'm going to do is I'm just going to take the magnets and I'm just going to drop them through the plastic tube. And you'll probably guess what's going to happen. They're just going to fall really quickly. So they fall basically at the same speed they would fall if they weren't in the tube at all. Okay. So plastic is not a conductor, it's an insulator. Currents don't flow in the plastic, and nothing happens when you drop the magnet through it. So similar diameter tube. It's copper, it's a good conductor. Copper is not magnetic, right? So the magnets don't stick to the copper. It doesn't matter which orientation I have. So it's not magnetic at all. All I'm going to do is drop the magnets through the copper, and they fall much more slowly. Okay, I could flip them over and drop them. It doesn't change anything. They still fall at the same rate. So copper is not magnetic, but it is a conductor. This effect of slowing down of the magnets as they fall is very similar, or is almost exactly the same as the effect that you're going to study in lab number 8. Okay, and so what I'd like to do is I'd like to talk a little bit about this Faraday effect and what you're going to do in the lab in some more detail. So let's see if we can get this tablet back. And oh, what's happening? Didn't I share my screen? Okay. All right, here we go. So, yeah, all right. Okay, so the observations that we made are the following. When the magnetic field passing through a loop of wire changes, we get an induced current. We'll call it I subscript IND for induced. So that's I induced in the loop. So we saw that explicitly with this demonstration with the coil and the LEDs attached to it. I can draw a version of that experiment. So let's imagine that we have this loop of wire here. I'm gonna see if I can make that look a bit better. We're kind of looking a little bit from the side. And what we're going to imagine is that we take a magnet next to it. Maybe this is the north pole of a bar magnet. And so the south pole is over on this end. And we're going to have magnetic field lines coming out of the north pole of the magnet. And so some of those field lines will pass through our little loop. And some of them won't pass through our loop. And that's fine too. So there's our magnetic field. And for this first case, what I'm going to imagine is that the magnet, so if the magnet is stationary, so if we keep the magnet stationary, then the field through the loop's not changing. And in that case, we saw that with our coils here, when I just put the magnet inside the coils, there's obviously magnetic fields passing through our loops of wire and nothing happens. So in this case, I induced is equal to 0. All right. So we'll now do the same thing, but this time we'll pull the magnet, or maybe we'll push it towards the loop. So here's going to be our north pole again. Here's our south pole. We initially have some magnetic field lines passing through this loop, and some that are just missing it, like so. But this time, we'll take the magnet and we'll give it a push towards the loop. So if we push the magnet towards the loop, the magnetic field increases through the loop, and we get an induced current that's not equal to 0. Okay, and in fact, the induced current would be, let's see, it would be something like this. So this would be our I induced. Well, that's kind of interesting because we know that if we have a current, that it makes its own magnetic field. So we have this kind of funny situation where we're using a bar magnet to induce a current in this loop, and that induced current makes its own magnetic field. And what happens is that the induced current makes a magnetic field that opposes the change in the magnetic field that's through the loop. So here we have the magnetic field increasing to the right. To oppose that change, the induced current creates an induced magnetic field that points to the left. Okay, so what we're going to end up with is a B induced that looks something like this. And so what I want to say about this is that the induced current creates its own magnetic field, which I'll call B induced, that opposes the change in B through the loop. Just as a preview of what we'll talk about later in the next week or two is that this Faraday's effect of inducing currents using magnetic fields is like perhaps the most significant technological application of the concepts that we're talking about, and probably by far. So all of the power that we use to, turn on our lights, operate our devices at home and work or wherever, charge your electric car, all of that power is generated using Faraday's effect. And we'll talk about that in the coming days or coming weeks. Okay, and so we saw this effect in the demonstration. So I move my magnets towards my coil and the red light comes on. Okay, so we get a current in one direction. So the reason I knew the direction of the current is because if I do right-hand rule, I require B induced to oppose the increasing field to the right. And so B induced must be left, and then my fingers curl in the direction of the induced current, which was the direction I drew. All right, you can maybe guess what we're going to do next is we're going to have the exact same setup, but we're going to pull the magnet away from our loop. And so we'll start with, here's our north and here's our south pole. And so we have some field lines that are passing through. And as we pull the magnet away, the strength of the magnetic field through the loop will get weaker. Okay. What's going to happen is that there will be an induced current and it will create a magnetic field that opposes the changing magnetic field strength through the loop. So if the magnetic field is getting weaker and it was initially pointing to the right, B induced is going to try to maintain what was initially there. And so it'll make an induced current that points to the right to compensate for the decreasing field due to the bar magnet that's moving away. And so we'll get, in this case, a B induced that points in this direction. So this will be B induced. Okay, and so what direction will the current be? Well, I want my induced field to point to the right. And so I put my thumb to the right and my fingers curl in the direction of the induced current. And that is in this direction. And so that's the opposite direction of the case above. Yeah, good. So when we pull the magnet away, we get an I induced that creates a B induced that tends to maintain the original magnetic field that was in the loop. And we saw that with the demonstration of the coil. So if I increase the strength of the field in the loop, we saw that the red light comes on. So if I start with this and pull it out really fast, we should see the green light, and there it is. Notice that if I put the magnet inside and take it out very slowly, then I change the magnetic field slowly. There is an induced current, but it's very weak, not enough to turn on those lights. So if you move it fast, that's when you see the lights come on. And the faster you move it, the larger the current would be. Okay, so what about this copper tube when we drop the magnet down? Okay, so for a magnet falling through a copper tube, well, let's draw this in cross-section. So I'm going to draw our copper tube, but I'll draw it as if it's been sliced in half. It hasn't been sliced in half, but we're just looking at a section of this as the magnet falls. And so this is the copper walls of our tube. So here's copper, and here's our, let me draw the magnet a little bit further down here. Here's our magnet. It's falling in this direction, so it has some velocity down. And then we'll make, say, a north and south pole, something like that. Okay, and so what we have are magnetic field lines from the magnet that are exiting the North Pole and entering the South Pole. Okay, so these field lines are kind of making these loops, but I'm just drawing what they look like near the surface of the magnet. Okay, so I want to imagine then what happens in this region of space below the magnet. Initially, there's no magnetic field there, but as the magnet falls down, we increase the strength of the magnetic field in a downwards direction. The copper is a tube, and so just like the coil of wire, it can support currents that form these loops around the copper ring, right? If we cut it along here. So because this is a conductor, it allows currents to flow. And so we're going to get an induced current in this region around the red section. And that current is going to make an induced magnetic field. Is that induced magnetic field going to point up or down? Yeah. It's going to point up, right? It's going to oppose the increasing magnetic field that's pointing downwards as the magnet falls. So as our magnet falls into the red region, we get an I induced that creates an upwards B induced to oppose the changing field due to the falling magnet. Okay, and so that's exactly what happens. We get a B induced that points upwards. But a magnetic field pointing upwards is kind of equivalent to placing a little bar magnet in this region that looks something like this. The magnetic fields leave the North Pole, so if I put the North Pole at the top, we get an upwards B induced. Okay, and so that means below the, if I want a B induced to point up, I put my thumb up, and the current around the copper tube is flowing into the screen on the right, and it's coming out of the screen on the left. And so what we must have is induced currents that are going into the screen here and coming out of the screen here. And so this is our I induced. All right, let's do the region that's just above the falling magnetic field. In this region, we initially had a magnetic field that was pretty strong and pointing down, but as the magnet falls away, the downwards field starts to decrease. And the Faraday effect says that the induced magnetic field that we get will oppose that change. So it's going to try to maintain the downwards magnetic field that was originally in place by making a field that points down. And that's equivalent to kind of having a little bar magnet in this orientation. So if I want a downwards magnetic field, by the right-hand rule, the currents are going into the screen on the left and out of the screen on the right. So we're going into the screen over, this is into the screen. And over here, we're coming out of the screen, I induced. So you get this kind of fun situation where below the magnet, falling magnet, you have currents making loops in one direction and currents making loops in the other direction above it, which make these induced magnetic fields that are in opposite directions. Now, let's look at this. We have the north pole of the falling magnet approaching the north pole of the induced magnetic field below. And so those two north poles repel one another. So that induced magnetic field, the red one, opposes or stops the magnet from falling, slows it down. Above it, the north pole of the green induced magnetic field is attracting the south pole of the falling magnet, and it's pulling it up. It's also stopping it from falling. Okay, so as the magnet falls away from the green region, we get our B induced that is pointing downwards to maintain the original magnetic field that was in the region. Okay, and these two induced magnetic fields, so both the top and bottom B induced, tend to slow the falling magnet. And this effect, you might call it something like magnetic braking. Okay, good. So you're gonna do something similar to this in lab 8. And so let me draw the geometry of your experiment. You're not gonna drop magnets down a vertical tube, but you're gonna slide magnets down an inclined plane, and that inclined plane will be made of these copper strips, okay? So lab number 8. So we slide magnets down a conducting track. And your conducting track will be copper. So let's take a side view of your apparatus. I'm going to draw the plane here. This is our copper track. And here is our magnet. And this magnet sliding down with some velocity v. And then let's just make north and south here. It doesn't matter. Okay. So what we have the North Pole facing our track. And so that means we're going to have here a magnetic field that's kind of pointing down into the track. And we could do the same sort of analysis that we did for the copper tube, right? We could pick a green region over here where the magnet was just in that vicinity. And so we had in that region a magnetic field that was pointing downwards. And then the magnet slides down. And so we have a decreasing downwards magnetic field in the green region. And so that means it's going to make a B induced. Sorry, that's wrong. We had a downwards field that was decreasing. And we're going to try to maintain what was there. So we're going to have a B induced that points downwards. Okay. If we have a B induced that points downwards, that's like having a bar magnet in here where we would have our north and south poles aligned in this way. So the south pole is on the top. And then we could go and we could look over here in this region. I should have made my magnetic fields not red. Here, let me clean it up. I want to make this consistent with the picture that we drew above. So this bar magnet, the sliding magnet, is making this blue field that points downwards. And that blue field is going to enter into this red region where originally there was no magnetic field. And so now we're going to have an increasing field that points into the copper. And the Faraday effect is that the induced magnetic field will oppose that change. And so we have to have an upwards be induced in this case. And that's like having a bar magnet where we have our north pole at the top. Let's see if I can make that look a bit better. So a north pole at the top and a south pole at the bottom. And we get the same sort of thing. The green region, the south pole near the surface of the copper attracts the north pole of the sliding magnet, and it tends to slow it down. The north pole of the induced field in the red region opposes the north pole of the sliding magnet, tends to slow down the sliding magnet. And so the two induced magnetic fields slow the magnet. Okay, what you're going to do is you're going to have these copper tracks. You're going to have copper tracks of different thicknesses, very thin one, a medium one, and a thick one, and you're going to slide the magnet down these tracks. You're going to record the motion of the magnet using a cell phone. We will provide the phone, and then you're going to analyze the motion. You're going to analyze these videos to see how the position of the magnet changes with time, and you're going to look at the different cases of thin, medium, and thick copper tracks, and you'll also slide down a plastic track which is not conducting and examine that case as well. So let's see what you should expect to find. Okay, so I'm going to draw this picture again, but we're going to, instead of drawing all the magnetic fields, I'm going to draw a free body diagram for the magnet. Okay, so here's our free body diagram. All right, and we'll say that this angle, the elevation angle of your track, is theta. So what forces are acting on the magnet? Just yell out one force. Normal force, okay. Normal force is always perpendicular to the track. Yeah, what else? Friction, okay. So this is going to be a sliding magnet. And so we're going to have some kinetic friction. What else? Gravity, okay. And so now we're going to have the gravitational force, mg. This angle here will be the same angle theta. There's one other force, what is it? Yeah, so we have these induced currents that are making these magnetic fields that interact with the magnet. Now, we don't have a nice way of writing down exactly what that force is, but one thing we have observed is that the faster we pull the magnet out, or the faster we move the magnet, if I move it slowly, there's no light. If I move it really fast, it's bright. And if I move it at a medium speed, it's kind of a dim light. So the faster the magnet is moving, the stronger this magnetic force. So what I'm going to do is I'm going to call this a drag force. And so this is our kind of new special force. So we'll call this like a drag force. So D is a drag force due to the interaction between B induced and the magnetic field of the magnet. Okay, like I said, we're not going to write down some like rigorous derivation of what this drag force is, but we know that the drag force will get stronger the faster the magnet moves. And so let's postulate that the drag force is proportional to the speed of the magnet. So this is the speed of the magnet. And this is going to be some kind of drag coefficient. Okay, so the idea is if the magnet is moving fast, we have a large induced current, which creates a large induced magnetic field. If the magnet is moving slow, it makes a small induced current, which makes a small induced magnetic field. Okay, so what we can do is we can just do force analysis here. So we would say the net force is equal to mass times acceleration. And let's do the y direction first. And so I'll make my coordinate system x, y. And in the y direction, there is no acceleration because we're just sliding down this plane, and y is perpendicular to the plane. There is no motion in the y direction, so this has to be 0. And so if we add up all of the forces in that y direction, we have the normal force upwards, and then we have, let's see, mg cos theta downwards. They have to equal 0, and so therefore our normal force is equal to mg cos theta. Okay, and now we have to do the x direction. So there's the y direction, the x direction, max. Well, this time it's not 0. The acceleration is not necessarily 0. We have magnets sliding down the slope of our ramp. So along the positive x direction, we have mg sine theta. And then in the negative x direction, we have the kinetic friction. The kinetic friction is the kinetic friction coefficient, mu k, times the normal force. And so this is the force of kinetic friction. And then we have minus the drag force, which we said was going to be B times V. And so this is our drag force. All right. So what we can do is we can sub in for our normal force. And we could say, all right, let's see. I'm going to have to add a page here. All right. Okay, so then we would say m times the acceleration in the x direction is mg sine theta minus mu k. And for the normal force, we get mg cos theta minus b times v. All right, what we could do is we could divide by m, and we can collect some common factors of g. So we would say ax is going to be, let's see, I'm going to divide by m. So we'll cancel, 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 and then we have to divide by m over here. And then we have a g, and then we have sine theta minus mu k cos theta, and then we have minus b over m times v. So this is the acceleration of the magnet. Okay. Now we have a couple of cases to consider here. So case 1. Let's imagine that we just want to do the simple case where you're going to have one plastic track. And so you drop your magnet onto the plastic track and it slides down. There is no magnetic drag force in this case. There's no magnetic braking. And so that means that this coefficient B would be equal to 0. If the drag force is 0 and the drag force is B times V, we know the speed of the magnet's not 0, it's sliding down the track. So the only way we have 0 drag force is if that coefficient was equal to 0. So if our track is not conducting, so this will be the case of the plastic track, then B is equal to 0, and AX is equal to G times, what is it, sine theta minus mu K cos theta. And if I look at everything in there, those are all constants. The gravitational acceleration is a constant, 9.81 meters per second squared. The angle theta of our ramp is a constant. Mu k, the coefficient of kinetic friction, is a constant. And so this is a constant. And we know when we have constant acceleration, we can describe the motion using our kinematic equations. So since AX is constant for this case 1, we can use kinematics. And we could say the position x of our magnet would be equal to 1/2 ax t squared. I'm assuming that we're going to start the magnet from rest. So there could be like a v0t plus 1/2 at squared. But if v0 is 0, then we can ignore that. So in this case, we expect x to be proportional to t squared. And when you do your analysis, you're going to measure the position as a function of time. And what you're going to find is, hopefully, the position will be this quadratic dependence on time. So this is x is proportional to t squared. Okay. Case 2 is the more interesting case. This is the one where you drop the magnet onto a copper track. So case 2 is we use a copper track and B is not equal to 0. Okay, in this case, AX is going to be equal to G sine theta minus mu K cos theta. This part is the same. And then we would have minus B over M times V. What happens in this case is you start the magnet from rest, and V is 0 or it's very small. So that means this first term dominates and your magnet starts to accelerate. It speeds up, its position increases. But as it speeds up, the minus v over mv term gets larger. If that second term gets larger, then the acceleration decreases. And so the magnet is still speeding up, but at a slower rate. And as it speeds up and up and up, then this acceleration gets smaller and smaller. Eventually, it goes to 0. And in that case, the magnet moves at a constant speed. This is the same thing when you did the coffee filter lab last year in Physics 111, or you talk about skydivers. They jump out of a plane, they speed up. As they move faster, the air resistance increases, their acceleration goes down. Eventually, their acceleration goes to 0, and they fall at a terminal velocity. Your magnet is going to do the same thing. It will speed up until it reaches a terminal velocity, and then it'll move at a constant speed. So in this case, the magnet speeds up. Let's say as the magnet speeds up, the acceleration approaches 0, and the magnet reaches a terminal velocity at Vt. So if it's moving at a constant speed, then the position is just equal to Vt times t. Okay, so we can think of two little subcases here. One is that B is small. In this case, the approach to terminal velocity is slow. And so what you'll observe is, as a function of time, you're going to measure the position of the magnet. It'll first approach terminal velocity, and then once it reaches terminal velocity, this will be a straight line. And so here, this is x is equal to Vt times t, and we're moving at terminal velocity. And in this region, we have our approach to terminal velocity, where the speed is increasing at a slower and slower and slower rate. Okay. The other possible case is B is large. So there's a lot of drag. What happens when you have a lot of drag is that the magnet reaches terminal velocity very quickly, almost instantly. So the magnet reaches the terminal velocity almost instantly. And in that case, if you were to plot the position as a function of time, it would just look like a straight line. And x would be proportional to t. So for a plastic track, we expect to see a quadratic dependence of the position on time. For a copper track, we expect to reach terminal velocity, and once we reach it, the position should increase linearly with time. The way that we change the strength of the drag coefficient B is by changing the thickness of the track. If you have a very thin copper track, thin materials don't allow for a very large current. It limits the size of the current. And so thin track corresponds to a small drag coefficient. And as you make the track thicker and thicker and thicker, the resistance to the currents gets smaller and smaller, the currents get bigger and bigger, the induced fields get larger, and you get larger drag coefficients. Okay, and so that's what lab 8 is all about. Thank you very much.